Hello friends, welcome to this session. In this session we are going to study some numerical problems on torsion. In the earlier video lecture we studied about the torsion equation, torsion formula, rigidity criteria equation, string criteria equation, and finally we have taken some of the numericals onto the torsion equation, and which we have found the maximum torque applied to the shaft. So in this particular video lecture, we will take some of the numerical problems onto the torsion. Let us take first problem. I will read first of all the problem. What should be the length of 5 mm diameter wire so that it can be twisted through one complete revolution without exceeding shear stress 40 MPa? Take G is equal to 2.7 into 10 raised to 4 MPa. So first of all, after reading, write the given values in the problem. So in the problem, the given diameter of the wire d is equal to 5 mm. Theta, this theta is nothing but the angle of twist. So this wire is twisted through one complete revolution. So twisting has been made to the wire after one complete revolution. Whenever the wire completes its one complete revolution, at that time the angle made or twisting angle of twist is made 360 degree. So that's why without given 360 degree, so by understanding this revolution, one complete revolution means there is a rotation of 360. That's why theta is value is taken 360. So first of all, convert that degree into radian by multiplying pi by 180. We'll get that value 6.28. And tau, that maximum shear stress or shear stress not exceeding 40 MPa. Sorry, here it is tau is by mistake it is written 50, so that tau is 40 MPa or 40 Newton per mm square. So G, modulus of rigidity or shear modulus, it is also called as, that G value is given 2.7 into 10 raised to 4 MPa. So first of all, they ask about what should be the length of 5 mm diameter bar. So diameter is given, but length of the wire is not given. So we will determine the length of the wire. So first of all, we know that torsional formula, our basic torsional equation is given. We know that, so it is T divided by J is equal to tau divided by R is equal to G theta divided by L. So we have taken here rigidity equation or rigidity criteria. So 40, that tau value is given shear stress divided by R radius, because diameter is given 5. That's why by dividing by 2 we'll get radius 2.5. G 2.7 into 10 raised to 4 into theta value 6.28 in radian divided by L. So we have taken the rigidity criteria equation. There is only one unknown, that is the length of the wire. So you solve this problem and calculate this length. So that length we get 10.59 into 10 raised to 3 mm, or converted into a meter, so 10.59 meters. So this is the final length of wire, which is 10.59 meter. Take second problem. A hollow steel shaft 3 meter long transmit a torque of 24 kilonewton meter. The total angle of twist is not exceed to 2.5 degree and allowable shear stress is 90 MPa. Determine inside and outside diameter of the shaft. Take G is equal to 85 MPa. So first of all, in the problem they given length of the shaft. So the shaft is hollow. There are two types of the shaft. One is the solid shaft and another is the hollow shaft. If the hollow shaft is there, definitely there are two diameter, external diameter and internal diameter. So this is a hollow shaft, and in the problem also they ask to determine the inside and outside diameter of shaft. So length is 3000 mm. Torque applied is 24 kilonewton into meter. Make it convert into Newton mm. So by multiplying 10 raised to 6, theta value 2.5 degree is given. So first of all, convert that degree into radian by multiplying pi by 180. We'll get this value 0.045 radian 44. Tau value, that maximum shear stress or allowable shear stress is given 90 Newton per mm square, and G is obviously given shear modulus and the capital D and small d, that is outer diameter and inner diameter, we have to determine. First of all, we know that the torsion formula T upon J is equal to tau upon R is equal to G theta divided by L. So we have to first of all determine the, because ultimately we want the diameter. So first of all we determine the polar moment of inertia by taking this rigidity equation T upon J is equal to G theta divided by L, because all the other values are known. So we first of all determine the polar moment of inertia. So T value, that is a torque applied, 24 into 10 raised to 6 is given. This pi by 32 d raised to 4 minus d raised to 4 is the total J, that is a polar moment of inertia. G, shear modulus of rigidity is given 85 into 10 raised to 3, and theta is converted into radian, that value is also there, divided by length of the shaft 3 meter means 3000 mm converted, and after solving this we'll get this J. It is nothing but the polar moment of inertia, 19.252513 into 10 raised to 6. So let us say this is as a first equation number 1. Let us move further. We know again the, as per the strength criteria, T upon J is equal to tau upon R. So tau max, obviously this allowable shear stress, divided by R is the radius of shaft, T is the torque applied, J is the polar moment of inertia. So 90 value, that is a tau value is given, R radius d by 2, that is the diameter divided by 2, and torque applied is given 24 into 10 to 6. J we already determined earlier as per equation 1. J value if you put, so finally we'll get the capital D. So this capital D is nothing but the outer diameter or outside diameter of the shaft, 144.38 mm. So put that value in equation number 1 here, because J is nothing but the pi by 32 d raised to 4 minus small d raised to 4. So if you put that capital D value, we'll get the small d, which is the inside diameter of the shaft. So that is capital D and small d are our objective, that diameter, that is outside and inside diameter. Let us take third problem. A solid circular shaft transmit 115 kilowatt at 300 rpm if permissible shear stress is 75 newton per mm square and allowable twist is 1.5 degree in a length of 3 meter. Determine the diameter of the shaft. Take G is equal to 82 into 10 raised to 9 newton per mm meter square. So in this problem they ask about the diameter of the shaft. So all the other given values, that is power transmitted by the shaft 115 kilowatt, length of the shaft is given 3000 mm, number of revolution by the shaft 300 revolution per minute, theta value 2.5 degree is given, converted into radian by multiplying pi by 180, you get that radian, and tau, that is allowable or permissible shear stress 75 newton per mm square. So as per this problem, the G is given, shear modulus or modulus of rigidity, make it convert into newton per mm square by multiplying this. So it is converted in 82 into 10 to 3 newton per mm square. So capital T, we know that torque transmitted by the shaft. Small tau is the intensity of the shear stress in the shaft. So first of all, we know the equation already, we derived or we have seen some of the important terms related to the torsion, that power transmitted by the shaft, and this symbolically represented by the capital P, and we know this particular equation 2 pi n T average. So this torque is the average torque and divided by 60. So this is the value is in second, this is the value, it is power transmitted by the shaft. So use this equation and put all this value, because P is already given, power transmitted 115 kilowatt, 60 divided by n, number of revolutions are also given, torque is not given here, so only one unknown is there, that is a torque. So you use this equation and determine the torque, this capital T. So after solving this, we'll get the torque 3.661 kilonewton into meter. So that kilonewton into meter, this value you can convert into newton mm. So by multiplying this 10 raised to 6, so we'll get the 3.661 into 10 raised to 6 newton into mm. So we know that the torsion formula, so this is the basic our torsion equation, that T upon G divided by tau upon R is equal to G theta divided by L. So we use this strength formula, tau max divided by R is equal to T upon J. Already we know that the polar moment of inertia pi by 32 d raised to 4, and the radius is the diameter divided by 2. So put this value, because tau max maximum shear stress is 75, radius diameter by 2, and torque we determined earlier that 3.661 into 10 raised to 6, that torque, and J is the polar moment of inertia, that formula is also known. So by solving this, there is only one unknown, that capital D you determine, and you can calculate this capital D value, that is the diameter of the shaft. So this diameter of the shaft we get by using this torsional formula, but in there is a strength equation or the strength criteria as per that formula. This is the strength criteria formula. So we'll get that capital D here, but we'll check that value by rigidity formula also. So by rigidity formula, the equation is like this: T upon J is equal to G theta divided by L. So putting all these value here, that G theta divided by L, T torque also we determine 3.66 into 10 raised to 6, and J is also there. So J means pi by 32 for solid circular shaft, d raised to 4. So here it is also there is only one unknown, that is the diameter of the shaft. So after solving this equation, we will get this diameter of the shaft, which is same as we have determined in the strength formula. So that D is same here. So that's it here, because firstly that first formula we taken, that power transmission by the shaft here. So you remember these all these terms, and again the torsion formula we have used, and the strength criteria equation. So that's it here. Thank you very much.